So, how to, as I said before, not every program can access hardware. Then how does the OS knows which program can access and which program cannot? So, so that we are going to do some hardware level changes. Okay. So let's say the problem is the distinguishing between the execution. And so while a certain program is in execution, there will be a user mode and a kernel mode attached to it. Okay. If let's say it is a normal program like browser, it will be in user mode. Okay. Now that the bit will be one. There will be mode bit. This is called as mode bit, and this sort of distinguishes whether it is in user mode or in kernel mode. So if it is in kernel mode, then it will have some special privileges that sort of helps a user or the application to execute some hardware level functions. So when the system call happens, there will be a shift in bit. Now let's look at this example. So this is a simple program that needs some content from a file and it has to write it to another file. Basically, we're going to copy and paste it somewhere else. It starts from here. So I have given all the numbers in an order. So the program follows the same structure. So first of all, in the user process, you're going to interact with the system, and there you're going to give an input file name. So the user the it will acquire a input file name, and you're going to give that file name in a way of prompt in the command shell. We know that shell takes some commands, right? And then now the shell will accept the input, and later you're going to give another output file. You're going to give it in a way in a return prompt, and it will accept the input again. Now you're still in user process, but you have the input name and the output name. Now we have to find the input file. Yes, now we have to find the input file. For that, we have to access the disk space. So now, because we are going to communicate with some lower level, like your hard disk, there is a shift in mode. Okay, now it's in kernel mode. This involves some file operations like open, create, read, write, close. Uh, so to execute this file operations, we have to request the OS to access disk and memory on behalf of the user mode. So the OS enter the kernel mode. And in here, first the OS will try to find the input file and open it. If the file is not there, then we are going to abort it. The program will stop running. So now, if we got the file, then we're going to create an output file. And when you're trying to create an output file, and if the name is already there, again abort it. If the file is already there, then abort it. We don't have to continue with the program. If step number 7 and 8 is successfully executed, we're going to step number 9, which is a loop. We are going to continuously read from input and we're going to write to output. So we are going to do this loop until this number 10, instruction number 10 fails. In what situation instruction 10 might fail? Let's say uh, there's the error in a script while reading. We are trying to open a file which has different permission. Uh, some sort of timing interrupt has happened. So there are multiple ways where a read attempt can fail. So if it fails, again exit the loop and abort it. If everything is gone well, and we have read the file and we've written it in the output file, now close the output file. Because if there were to be another program which is trying to access, yeah, again, where this is also a situation where a read attempt might fail because that the file you're trying to read from is accessed by some another process. okay, and the process currently writing something. So in that way, the read file will be closed. I'll draw and show you. This is a file. This is a process two. Okay, and it is accessing it and it is writing something. So while this is happening, this whole thing is going to be exclusive. This is going to be separated. If process one has to approach file, it can't. It can't. Because now this file is not shared. So this is where a read attempt can fail. So the close the output file is because the other programs want to use it in the future. Now change the bit mode again. We are going to go to user mode. Bit mode is changed. Show the completion message to the user and terminate the whole program normally. So this is how the user and kernel will communicate between each other, and the kernel will communicate with the hardware on behalf of the user. So why this sort of modularity comes in? So if the user does some shenanigans like encroaching on the space that is not allowed to them, or trying to read data from another app, the OS will put a check and trap if necessary. So the that process which is going out of whack, it will be silently killed, and there will be no problem for other programs. So and once the program is silently taken off, you will be given an appropriate error message, right? This is what a system call does. Okay. There will be examples of system calls we'll look in for the lectures. Now I'm going to address a problem in having a shell separate from the OS. Okay, this is the OS, this is a shell. The shell is going to call exec. Exec is a system call. Okay, and the exec is going to basically exec loads an executable. Let's say if I'm saying exec browser, it will find the browser and it will load the browser into memory. So is calling some app, the shell is calling some app. The shell will exit and this becomes a browser. Hmm? The shell is trying to call a browser. Now here the problem is uh, the shell is calling some other program and the shell is gone. The shell is exit. And how will the shell come back? So this is like saying I'm calling someone and I'm gone. Now, how will I come back? So there is a problem with shell, and we already know how a shell calls loads a program, loads a new program. And we're going to look at one another system call. It's called fork. It creates a new process. Perhaps this fork will help us to rectify this trouble. Let's say, OS hardware. I'm going to restructure this again. So we have the shell running here, and the shell does fork. Okay, instead of exec, we're doing fork. Immediately, it will call the shell a replicate. Actually, the fork is going to replicate the shell, and this shell program is going to call exec. Let's say Spotify. Okay. Now, what happens is the moment this shell calls fork, it doesn't exit, but it gets blocked. Okay, it is still somewhere in the memory. Okay, it gets blocked for a temporary period of time, and this shell becomes Spotify. Okay, now the app is running. Uh, Things are done. Spotify exits. This work is done. Spotify exists completely. Now the control will come back to the shell, and this is not blocked anymore. Now the shell is safe. So this sort of idea, how will we differentiate from one shell with another? Because the fork uh, technically creates an exact replica of shell. So we have something called the PID, which is also known as the process ID, and we can give it zero, and can we give it some another number. So with this, we can differentiate between the shell. This is the parent shell, the technical parlance, and this is the child shell. We can differentiate it. So this is like saying we have all watched Ben 10, and if you have not watched Ben 10, then I'm sorry you had a boring childhood. So the Ben, he has a watch. I'll just easily summarize it for you. And there's a problem. Okay, he'll turn into an alien. Okay, let's say this is forearms. Once the problem is solved, the forearm has taken care of this and he'll come back to normal. So this is what a shell does. So when you type a command, the shell creates a copy of itself. Okay, it's called fork. Then the copy switches into a program you asked for via exec, the system call. Now the original shell waits quietly somewhere. Okay, once the program finishes, the shell wakes up and says, "What's next?" So that's the basic idea of having fork and shell. Now we've looked at certain OS components, and no matter what kind of OS we are going, all these components are going to be similar. So similarly, with the help of these components, different types of OS perform different functions. It performs some services. So that topic is called operating system services. This we will look at the next lecture.